Imagine managing millions of fans across three nations where every millisecond of latency counts and failure isn't an option. Welcome to the series Tech Behind FIFA World Cup 2026 System Engineering. My name is Kabir Anand. This is episode 2, and in this episode, we'll walk through running FIFA 2026 across three countries with multi-region architecture as a case study. Since operations span the US, Canada, and Mexico, we'll analyze how to build resilience when regional infrastructure fails. This framing helps us reason through whether an active-active or active-passive model actually works at this massive scale. It starts by breaking down the North American challenge, where we've got to orchestrate systems across different infrastructure zones and legal jurisdictions in the US, Canada, and Mexico. We'll explore why moving beyond single data center thinking is a must for global events, focusing on two main engineering goals: slashing latency for fans and ensuring geographic fault tolerance. To do that, we compare two primary deployment models, active-active and active-passive, while weighing the trade-offs of regionalized storage against centralized data. You'll see how cross-region synchronization and automated failover keep the experience seamless, even if a regional cloud provider fails or a major fiber trunk goes down. Since we are operating across three nations, we also dive into data sovereignty and how that impacts replication rules. Now, because this is a massive real-world event, we'll be careful to distinguish between documented public facts and what a plausible engineering interpretation looks like under this kind of pressure. By the end, you'll understand how to evaluate different deployment patterns and choose the right one for high-stakes multi-region environments. Let's set the scene with the actual engineering situation we are facing. Imagine millions of fans trying to access ticketing, live stats, and video highlights simultaneously across three different countries. We aren't just talking about a few servers here and there. We are talking about managing traffic across 16 different host cities spread over thousands of miles. What matters here is that the physical distance between a user and the data center creates a lag that can break real-time features. If a fan in Guadalajara is hitting a server in Virginia, the round-trip time alone can frustrate them. A major failure mode here is the thundering herd problem, where a sudden goal or a match end triggers a massive spike in requests that overwhelms a single region. We've to design for these bursts of activity while navigating different ISP reliability levels and international data transit issues. In practice, this means building a system that can absorb these shocks locally before they ever reach your core database. It's about building for the worst-case scenario while delivering the best-case experience. Now let's dive into the core of orchestrating this multi-region architecture. For a world-scale event like the 2026 tournament, we've to move beyond the traditional single-region mindset. This works by deploying independent copies of our application stack into multiple geographic zones, such as North, West, and Central regions across the continent. What matters here is that it allows us to handle traffic locally, which is essential when you're serving millions of concurrent users. For example, when a match kicks off in New York, the local regional stack handles the surge and telemetry data without taxing the resources in Mexico. The failure mode to watch out for here is configuration drift, where one region's settings start to differ from another, leading to unpredictable behavior during a failover. If the US East region has a different caching policy than the Mexico Central region, users might see inconsistent data. We look at how to use infrastructure as code to keep these environments identical, ensuring that the fan experience remains seamless regardless of which country the request is coming from. The North American challenge is unique because we are operating across three distinct nations: the US, Canada, and Mexico. This isn't just a matter of geography. It involves navigating three different infrastructure zones and legal jurisdictions. Physical distance is the first hurdle, as there are thousands of miles of fiber optic cable between Vancouver and Mexico City. What matters here is that network packets can only travel so fast, and every extra mile adds milliseconds of delay. In a real-world scenario, a media stream might look great in Dallas, but buffer constantly in Toronto if the source is too far away. Another failure mode is the variation in local infrastructure quality. One country might have more robust backbone providers than another, leading to uneven performance. There are also regulatory requirements to consider, which we'll discuss later. You have to account for these environmental differences by designing a system that's resilient to regional fiber cuts or power grid failures. It's about acknowledging that the network is never as reliable as we want it to be, especially when spanning an entire continent. To tackle this, our multi-geographic system design requires a fundamental shift in how we think about scale. We have to move from local scaling, just adding more servers in one spot, to global orchestration. This works by implementing a global control plane that manages how state and traffic move across continental boundaries. What matters here is that it prevents any single region from becoming a bottleneck or a single point of failure. There are three core components we have to get right: global traffic management, cross-region data replication, and regional isolation. For instance, if the ticketing service in the US region becomes overloaded, the system should intelligently route new requests to the Canadian or Mexican regions. However, a major failure mode here is split brain syndrome, where two regions lose connectivity and both think they're the primary source of truth, leading to data corruption. We manage this by using consensus algorithms and clear failover protocols. By moving beyond single data center thinking, we ensure that the entire system can survive the loss of an entire geographic area without impacting the global user base. So, why do we actually invest in the massive complexity of multi-region systems? Well, it really comes down to two primary engineering goals. First, we need to reduce the physical distance to the user, which we call latency reduction. Second, we have to ensure the system survives a regional catastrophe, which is resilience. These matter because they directly impact both the user's perception of the app and the overall reliability of the tournament's digital operations. For example, if a major cloud provider experiences an outage in the US, we need the Mexican and Canadian regions to pick up the slack instantly. A common failure mode during this transition is capacity exhaustion. If the remaining regions aren't scaled to handle the redirected load, they'll crash too, causing a cascading failure. We mitigate this by maintaining headroom or spare capacity in every region. By focusing on these two pillars, we are building a system that's both fast and indestructible. It's a trade-off between the cost of running multiple regions and the catastrophic cost of a total tournament blackout during a semi-final match. Let's look closer at our first goal: reducing latency. This works by placing compute power and data as close as possible to the fans in cities like Mexico City, Vancouver, or New York. By doing this, we minimize the speed of light delays that are just part of the physics of cross-continental networking. What matters here tremendously for real-time services like ticket scanning at the stadium or live match updates. If a fan in Mexico City tries to check into a stadium and the request has to travel all the way to a server in Virginia and back, that delay can cause huge queues at the gate. A failure mode here is a cache miss latency, where the local region doesn't have the data it needs and has to fetch it from a distant primary database, defeating the whole purpose of the local deployment. To avoid this, we use aggressive local caching and edge computing. In practice, this ensures that the system responds in milliseconds, making the app feel local and snappy, which is exactly what fans expect during a high-energy event like the World Cup. Our second goal is improving resilience, which essentially acts as a massive safety net for the entire operation. This works by having redundant stacks across the three host nations. If a regional cloud provider or a major local fiber trunk fails in one country, the system stays operational by shifting the load to the other two. What matters here is that at this scale, hardware and network failures aren't just possible, they are guaranteed. For example, during a peak game time, a sudden power outage in a major data center hub could take out thousands of servers. Without a multi-region setup, the entire tournament's digital platform would go dark. The main failure mode to guard against here is failover loops, where a system keeps trying to move traffic to a region that's also struggling, creating a cycle of crashes. We use automated health checks and circuit breakers to prevent this. By designing for this level of fault tolerance, we ensure that even a national level infrastructure crisis doesn't stop the game from being broadcast or the fans from using the app. Now, when we get into the actual implementation, engineering teams have to choose between two primary deployment models: active-active and active-passive. This is a critical decision that dictates how traffic is balanced across your regions. In an active-active setup, every region is handling live traffic simultaneously, which provides the best performance and utilizes all your hardware. In contrast, an active-passive model has one primary region doing the work while the others just sit on standby, ready to take over if things go wrong. What matters here is that it affects everything from your monthly cloud bill to how fast you can recover from a crash. For instance, an active-active system can handle a sudden spike much better because the load is already distributed. However, the failure mode for active-active is significantly higher complexity in managing data consistency across those regions. Active-passive is simpler to build, but you're paying for servers that are doing nothing most of the time. We'll look at the trade-offs of both so you can see which one fits the extreme demands of a global tournament. Let's focus on the active-passive architecture for a moment. This model designates one primary region to handle all the traffic, while the others are essentially in a warm or cold standby state. It works by having a global load balancer point everyone to the primary side, with a manual or automated trigger to flip the switch if that side fails. What matters here is that it's much easier to keep data consistent when you only have one source of truth. You don't have to worry about two users in different countries trying to buy the same last seat at the same time and causing a conflict. However, the failure modes are quite significant. First, there's cold start latency, where it takes several minutes for the passive region to spin up and handle the load. Second, there's the risk that the standby region isn't actually configured correctly because it hasn't been tested with live traffic. In a high-pressure scenario like a FIFA match, those minutes of downtime while you're switching over can be devastating for the brand and the user experience. Where your data lives is probably the most important decision in your entire stack. We have to evaluate the trade-offs between centralized storage and regionalized distribution. In a centralized model, all regions talk back to one master database, which simplifies consistency but creates a massive latency bottleneck for distant regions. In a regionalized model, each country has its own local data store. What matters here is that it directly impacts the performance of every single API call. For example, if a user in Mexico updates their profile, a regionalized setup makes that change instant for them. But if you're using a centralized database in the US, they'll feel a noticeable lag. The primary failure mode for regionalized storage is data divergence, where the Canadian database and the Mexican database end up with different versions of the same user's info. We have to use sophisticated synchronization strategies to keep everything in sync. Ultimately, we are balancing the need for speed with the absolute necessity of a single accurate version of the truth across the entire North American continent. To get that local speed we need, we often turn to regionalized storage through sharding or replication. This works by partitioning data so that fans in Mexico have their records stored in the Mexico Central region, while US fans are stored in US East or West. What matters here is that it drastically reduces the time it takes to perform actions like stadium check-ins or processing local merchandise sales. For instance, when thousands of people hit the gates at once, a local database can handle those writes in milliseconds. However, this requires very sophisticated conflict resolution. A major failure mode is cross-shard queries. If a fan from Canada goes to a game in Mexico, the system might have to jump between regions to find their data, which can be slow and error-prone if not handled correctly. We use global indexes and smart routing to minimize this. While it's more complex to manage, this regionalized approach provides the highest level of performance for localized services, ensuring that the infrastructure doesn't become a bottleneck during the busiest moments of the tournament. To keep all these regions updated, we have to implement cross-region synchronization. There are two main approaches here: synchronous and asynchronous replication. Synchronous replication ensures that data is written to all regions before the transaction is confirmed, which guarantees consistency but is incredibly slow over long distances. Asynchronous replication prioritizes performance by confirming the write in one region and then syncing it to others in the background. What matters here is that it's the difference between a system that's always accurate but slow and one that's lightning fast but occasionally shows slightly old data. For example, a fan might see a ticket sold status a few seconds late with async sync. The failure mode for asynchronous replication is data loss during a failover. If the primary region crashes before it can sync its latest updates to the standby, that data might be gone forever. We have to carefully choose which parts of the FIFA system need absolute consistency, like financial transactions, and which can handle a bit of lag, like social media feeds or fan comments. Failover design for disaster recovery has to be almost entirely automated at this scale. We use a combination of continuous health checks and global traffic managers to detect when a region is struggling. When an outage is detected, the system automatically reroutes millions of fans to the remaining healthy regions. What matters here is that a human can't react fast enough to a regional fiber cut in the middle of a championship match. For example, if the US East region goes down, the global DNS should instantly start sending those users to the US West or Canadian regions. The failure mode to watch for here is the false positive, where a temporary network glitch makes a region look down, triggering a massive unnecessary move of millions of users, which can itself cause an outage. We use quorum-based sensing to make sure a region is actually dead before we pull the plug. This creates a circular loop of monitoring, detection, and redirection that keeps the tournament's digital heart beating even when a whole country's infrastructure is under fire. We achieve proximity routing using technologies like Anycast or GeoDNS. These work by detecting the user's IP address and automatically routing their request to the closest host country to minimize network hops. What matters here is that it's the most effective way to optimize latency without changing a single line of application code. For example, a fan in Monterey will naturally hit the Mexico City data center rather than one in Montreal, purely because it's the shortest network path. A failure mode here is geo-misclassification, where a user is routed to a distant region because their ISP's routing tables are messy, leading to a poor experience for no obvious reason. We also have to consider Border Gateway Protocol or BGP hijacks, which can maliciously reroute traffic across the globe. By using a combination of Anycast for entry points and GeoDNS for service discovery, we create a pathway that ensures fans always take the fastest route into the system. It's about making the network physics work for us, not against us, across the vast North American landscape. Operating in 3 different countries means we have to respect 3 sets of data laws. Data sovereignty is a huge deal here. It's the requirement that certain sensitive information, like personal fan data, remains within national borders. This works by setting up strict replication rules that prevent Canadian user data from being permanently stored on US servers if the law forbids it. What matters here is that failing to comply can lead to massive fines or even the shutdown of the service in that country. For example, Mexico might have specific privacy protections that differ from the US, requiring us to shard our databases along national lines. A failure mode here is compliance leakage, where a backup or a log file containing sensitive data is accidentally copied to a region where it shouldn't be. We use encrypted data enclaves and strict access controls to prevent this. This adds a layer of complexity to our replication strategy as we have to balance the technical need for global data with the legal need for national isolation. It's a perfect example of how law dictates architecture. Our ultimate engineering focus is geographic fault tolerance. We want a system where the loss of an entire country's infrastructure doesn't stop the game. We design for blast radius isolation, which means we ensure that a fault in Mexico doesn't cascade into the US or Canada. This works by using 3 main strategies: independent regional stacks, bulkhead patterns in our APIs, and graceful degradation. What matters here is that it prevents a local issue from becoming a continental disaster. For instance, if a database in Toronto becomes corrupted, we want to make sure it doesn't replicate that corruption to the New York or Mexico City databases. A failure mode here is shared dependencies, where all regions rely on a single global service like an identity provider that, if it fails, takes everything down at once. We mitigate this by regionalizing even our most core services. In practice, this means even if one host nation has a total digital blackout, the other 2 can continue to serve the millions of fans who are still online and ready for the match. Now let's have a reality check. In large-scale events like this, there's always a gap between what we see in textbooks and what actually happens in production. As engineers, we have to look at what we know is possible versus what's kept under the proprietary hood of organizers like FIFA. While we can design a perfect multi-region system on paper, the real-world implementation is often constrained by legacy systems, budget limits, or specific vendor contracts. What matters here is that it reminds us that design is always about trade-offs. For example, a pure active-active setup might be too expensive to maintain, so a hybrid approach is often used instead. A failure mode in this assessment is over-engineering, building a system that can survive a meteor strike but is too slow for daily use. From a systems design perspective, what's publicly known is that they need high availability, and we can infer that a multi-region strategy is the only way to achieve it. We are using our engineering logic to fill in the gaps where the official documentation might be a bit thin. We can be certain that multi-country operations are a requirement, not a choice. The physical logistics of the 2026 schedule, with games happening across the US, Canada, and Mexico, demand that the API and data layer exist in multiple jurisdictions simultaneously. This works because the sheer volume of traffic and the geographic spread make a single region deployment physically impossible for delivering a quality experience. What matters here is that it forces us to solve the hard problems of distributed systems, like latency and state synchronization from day one. For instance, the ticketing platform has to handle users from 3 different currencies and tax systems in real time. A failure mode here is jurisdictional latency, where legal checks between countries slow down a simple user request. We know from previous large-scale events that the physical footprint of the tournament dictates the digital footprint. In 2026, that footprint is continental, meaning our infrastructure has to be just as widespread to ensure every fan, whether they are in a stadium or at home, gets throughout the entire month of competition. While the principles of multi-region architecture are clear, the specific implementation details for an event like the 2026 World Cup are often undisclosed and proprietary. We rely on industry standards and postmortems from other massive events to infer the likely technology choices. For example, while we don't know exactly which database technology is being used, we can assume it's something that supports global distribution, like Spanner or Aurora Global. What matters here is that it helps us understand the state of the art even when we don't have the blueprints. A failure mode here is assuming that the organizers are using a specific silver bullet technology when in reality, it's probably a complex mix of many different tools and custom-built solutions. This part of our study is an engineering interpretation. We look at the requirements, high availability, low latency, and regulatory compliance, and we map them to the best known patterns in the industry. It's about building a mental model of a world-class system based on the constraints we know are real, even if we can't see every line of code or every server rack. In an engineering discussion, a common question is, when would you choose an active-active over an active-passive deployment? Well, you should choose active-active when your recovery time objective or RTO must be near zero and regional latency is absolutely critical. This works by keeping all regions live and ready to absorb traffic at any moment, which is what you'd want for a live match broadcast. On the other hand, you should choose active-passive when cost is a major constraint or when your data consistency logic is too complex for multi-master writes. What matters here is that an active-active setup is much harder to build and maintain, especially with data conflicts. For example, if you're managing a global leaderboard where every millisecond counts, active-active is the way to go. But if you're managing a simple content site where a few minutes of downtime during the switch is acceptable, active-passive is far more efficient. A failure mode for active-active is the high cost of synchronization, while for active-passive, it's the risk of a failed transition. It's always a balance between the complexity you can handle and the performance your users demand. We've just unpacked the massive technical footprint required to run FIFA 2026 across the US, Canada, and Mexico. Designing for this scale means moving away from a single data center mindset to a true global orchestration. We focused on two main engineering goals here. First, slashing latency by placing compute closer to fans in cities like Mexico City or Vancouver. And second, building resilience so a regional outage doesn't take down the whole tournament. To achieve this, we looked at two deployment models. Active-passive keeps things simple with a primary site but leaves resources idling, while active-active serves traffic from everywhere at once. It's a classic engineering trade-off where you're balancing data consistency against immediate performance across a whole continent. And getting that right is what keeps the system standing under pressure. That wraps up our look at multi-region architecture for the 2026 games across the US, Canada, and Mexico. We've explored two primary deployment models, active-active and active-passive, and how choosing between them dictates your system's resilience. While the exact internal setup for the tournament isn't public, we've modeled a plausible architecture that addresses the massive geographical blast radius and data sovereignty needs of three different nations. In the next episode, we'll talk about scaling FIFA matchday traffic with load balancing and look at situation, core understanding, and purpose. Quick question for the comments. If you're prioritizing strict data consistency over low latency for ticket sales, would you lean towards synchronous or asynchronous application? Catch you in the next one.